So the first one up there are solutions. I realize you guys are probably getting tired of seeing these by now, but no, keep them coming. Remember, the first thing we have to ask is, what are the 2% that we are mixing? (32 and 56). Very good. And we're expecting to get a result of 40%. What amounts do we know? 120 milliliters goes with 56. So if we let the amount of 32 be X, how much 40% do we have? X plus 120. So that means our equation, 32 times X is going to be 0.32 times X plus 56% times 120 will be 0.56 times 120 equals 40% will be 0.40, or just 0.4 if you want to, times X plus 120. So the 0.32X won't change. 0.56 times 120 is 67.2. Here we're going to have to distribute through the parentheses. So 0.4 times X is 0.4X. 0.4 times 120 is 48. X appears twice, so we need to get rid of one and we'll get rid of the 0.32. Exactly. So we have the 67.2 on one side. 0.4 minus 0.32 is 0.08X plus 48. We'll subtract the 48. We've got 19.2 equals 0.08X. And then divide by the 0.08. Bless you. 240 milliliters equals X. We should always double check to make sure that's what we're asked. X, 240 milliliters is the amount of the 32%. And we're asked how much 32%. So that's what we're looking for. Any questions on that one? Are we feeling a little bit better about those yet? Okay. Sorry. Number 2, an IV has infused 1,680 milliliters of fluid in 7 hours. What is the total time required to infuse 4,800 milliliters of fluid? So we've got 1,680 milliliters in 7 hours. That's a rate because the units are different, but it doesn't matter. We can still use a proportion. The 480 milliliters has to go where? Or 4,800, I should say, on top. Because when we have units, when we have rates that have the units in there, the labels have to match up from one rate to the next. So now it would be 7 times 4,800 divided by 1,680. That sounds about right. Yep. Did you divide this out to get 240 milliliters per hour? Okay, good point. In these proportions, yep, and that's exactly what works exactly right. In these proportions, there are two relationships. The 1,680 milliliters and the 7 hours are related because they're measurements at the same time. The 1,680 came at 7 hours. Well, the 4,800 and the 20 hours, they're related because that's the full amount and the full time. So those relationships can either stay vertically one above the other like this, But you remember, we also had the relationship going this direction where they're both milliliters, and here where they're both hours. As long as we maintain those relationships, it doesn't matter what direction they go. So this relationship could go this way. Yep. Yep. As long as the 1680 and the 4800 go together in one direction and the 1680 and the 7 hours go together in one direction, it doesn't matter. Okay, the survival rate of critical care patients is 95%. So 95% means we have 90. Yes. I think I hear somebody asking a question, but can't hear you. I don't know what I'm hearing. Is somebody asking a question, or is that some stray noise coming in from another room? Sorry, the system, for some reason, the sound is really muffled. If somebody's asking a question, give me a wave. Oh, there you are. Okay. Can I have you sit closer to the microphone or something? Because for some reason, I just can't hear you. You happen to be right behind my picture in picture right now, so there you are. We'll see if we can turn up the volume on your end of the mic. Now I can hear you. Yes. Okay. So I can hear something muffled, but okay. The 20 hours when we have, let me see if I can erase some of this mess here. When we have a proportion like this, the way we find the missing number is there are always going to be two diagonals. The diagonals go like that and like that. Well, one diagonal has both numbers on it, and that's the 7 hours and the 4,800 milliliters. So we would multiply those. 7 times 4,800 gives us the 33,600. And then we divide by the number that's on the other diagonal, the 1680, which gives us the 20. Or the other way you could do it is you could put an X in here, then you can cross multiply both directions. So you have the 7 times the 4,800, which is still 33,600, equals, then going this direction, it's 1,680 times X, and you can just solve that equation for X. Does that make more sense? Okay, perfect. Oh, sure. Sorry about that. Okay, so for the critical care patients, 95% is 95 out of 100. Out of 820 patients, I kind of forgot how many are expected to survive. So out of the 820, where would the 820 go in our proportion here? Bottom. Because if I look at my percent here, 95%, the 95 represents survivors. The 100 always represents everybody. That's all of them. So 820 is all of them. How many are expected to survive? We will just cross, multiply, and divide. What's that? 779? That sounds right. 779 survivors. Any questions on that one? Okay. because you have to divide by 100. Yeah, get rid of the 2 zeros. You're there. It's okay. You're close. You've got it. Okay, so closely related to these proportions and other things is going to be our unit conversions. But before we dive into our unit conversions, our measurement conversions, I want to talk a little bit about something called dimensional analysis. Dimensional analysis is a very big word for an extremely simple but very, very useful tool. What dimensional analysis basically is carrying the units through and dealing with them. You know, for example, let's say you drive 50 miles per hour, mph. How far would you go in 6 hours? Well, most of us know how to calculate this, but we can use the dimensions to help us. 50 miles per hour, we were saying with our rates and ratios, that has to be thought of as being 50 miles over 1 hour. 6 hours, I'm going to make that into a fraction. 6 hours over 1. Now, you might be thinking, how can it be simpler by making it into a fraction? Well, because now I can use my units, my dimensions. In my fractions, the hours, the units for hours is going to cross cancel out. So now I have 50 miles on top times 6. That's 300 miles. And on bottom, I have 1 times 1 is 1. So that's just 300 miles over 1 is just 300 miles. So in 6 hours, driving at 50 miles per hour, you'll go 300 miles. The units tell us that's worked out. The units work out, so it tells us that we probably did the formula the correct way. If you're looking at a pressure, let's say your pressure is 80 psi. What area is required? There we go. For 720 pounds of force. So again, our units are going to help us figure out how to do this. 80 psi is 80 pounds per 1 square inch. We have the 720 pounds. I'm going to make that a fraction by putting it over 1. We are looking for area here. If we're looking for area, that means we want our answer to be in what units? Inches squared, square inches. So we need to get a result that's square inches here out of these units. That means that somehow the pounds have to cancel out, and we need to have the square inches on the top of the fraction. Well, the only way we're going to do that is to take our 720 pounds and divide by the 80 pounds per 1 square inch. And the reason that's going to work out, because of what we know for fractions, when we divide, we're actually going to multiply by the reciprocal. And we can see now that the pounds cross cancel out in our fractions. 720 times 1 square inch is 720 square inches. 1 times 80 is 80. We can divide that out. 720 divided by 80 is 9 inches squared, or square inches. That's all dimensional analysis is making sure the units work out. I mean, many of you may have known that if you take your force and divide by your pressure, you're going to get an area. Well, putting the units in here and double checking, Yeah, it proves it. The units work out and we get square inches. We get an area unit in our result. So that tells us that we most likely did that calculation correctly. I would say 99% of problems that involve measurement, if you double check with the units, if the units work out, the answer you get is going to be correct. When we get into dosage calculations in our next unit, in unit 3, I use a lot of dimensional analysis. The textbook covers other ways of doing it. But if you get good at dimensional analysis, you really don't even need to understand the materials you're working with. The units will tell you what has to be done to convert everything over. Yes. Because this is multiply and not equals. That's a very good question, though. That's something that does confuse a lot of people. Why didn't we have to line up hours here and hours here? Why could we have them diagonal? Well, there's two different things. A proportion is one fraction equal to another fraction. And if you have that equal sign in there, let's put some numbers in there. When you have that equal sign in there, then you do have to line up. There has to be a relationship here and here. And then, of course, there has to be a relationship going the other direction, here and here. And then you would solve that by cross multiplying. The cross product should be equal, or you can cross multiply and divide to find the missing number. Dimensional analysis, we are multiplying fractions. It's one fraction times the next fraction. So we have 70 pounds over 1 square inch times 5 square inches. Because we're multiplying, the units don't have to line up. In fact, we want them to cancel out, so we want them to be diagonal so that we can cross cancel the units. Now, your textbook takes dimensional analysis to a little bit of a strange place, to quite an extreme, to be honest. In your textbook, it takes dimensional analysis to problems that would not be practical. I mean, practical type problems would be kind of similar to what we were doing up there with the miles per hour and how many hours. You know, if you have an IV flowing at 35 milliliters per minute, how much is going to flow in 2 minutes? Well, same type of thing. You got your 35 milliliters over 1 minute. If you multiply by 2 minutes over 1, the minutes are going to cancel out. You're going to get a result that is milliliters. Or if you want, we're trying to convert. If you have units that are milliliters per minute, and you need to switch it over to drops per minute, you would use a unit that has drops related to milliliters, so the milliliters will cancel out, and you can multiply across, and you're going to have drops on top and minutes on bottom. It's going to be drops per minute. Those are the practical uses of dimensional analysis. Like I said, your textbook takes it to the extreme, and I get why. It's trying to make this something that, by making you do these extreme examples, is trying to make the simple ones easier for you. But it uses things like this. You know, a centimeter to the negative 1. Well, what does it mean to have something to the power of negative 1? It's a vacuum? Yeah, it does. You're exact. That's one way of putting it. I said I never heard that term attached to it, but I get what you're saying. Yes, it's actually removing it, kind of. If we looked at something like x, let's put a number in here. I prefer working with numbers. Like 5 to the third power is 125, right? 5 times 5 times 5. 5 to the second power is 25. And 5 to the first power, of course, is just 5. What's 5 to the 0? Most people want to say 0, but it is 1. If we look at our pattern, every time that power reduces by 1, this result is divided by 5. Right? 125 divided by 5 is 25. 25 divided by 5 is 5. 5 divided by 5 would be 1. If we kept going, 5 to the power of negative 1, well, 1 divided by 5 would be 1/5. 5 to the power of negative 2, that'd be 1/25. 5 to the power of negative 3 is 1 over 125. And what you see as we do this is the negative powers are related to the positive powers. They're just reciprocals. 5 to the power of negative 2 is just the reciprocal of 5 to the second power. 5 to the power of 2 is 25. 5 to the power of negative 2 is 1 over 25. So centimeters to the power of negative 1 is really a reciprocal, or 1 over centimeters. So what that means, if I have centimeters to the power of negative 1 times regular centimeters, what do I get? Well, centimeters to negative 1 is 1 over centimeters. Regular centimeters, I can treat as centimeters over 1. I cross cancel the centimeters. You get 1 and 1. Yeah, 1 times 1 is 1 over 1 times 1 is 1. So it's just 1. Everything cancels out. So centimeters to the negative 1 times centimeters is 1. I use that example, centimeters to the negative 1, because there actually are places in physics where, in chemistry, where a length to a negative power does occur. Elastic modulus, and Young's modulus, and stuff like that, you do get negative exponents on a length. Yeah. Centimeters to the negative 1 is just 1 over centimeters. It's still positive. The negative, like this is not a negative 1/5, it's still a positive 1/5. Even though it's 5 to the negative 1. The way to think about it is the negative power means you're dividing by it instead of multiplying by it. On the test I want to give you, there will be some homework where it asks you to do them. Yeah. The textbook does something silly like this, like grams to the negative 1. Well, I have never in my life seen anything where there's a negative power on a mass unit. But of course, grams to the negative 1 just means 1 over grams. And then, of course, your textbook is going to ask you to do some problems that might look like this. Milligrams over liters times centimeters squared times actually there. Again, I realize this is an extreme example, but this is what the textbook is doing. You can cross cancel, the liters cancel out, the milligrams cross cancel out. So what we're left with here is 1 over centimeters squared. Well, centimeters squared, of course, is centimeters times centimeters. And then, of course, on bottom, we're still going to have times that centimeters to the negative 1. Well, what would happen is, of course, the reciprocal of centimeters, or centimeters to the negative 1, is going to combine with 1 of the centimeters and cancel out. On top, you have 1, and on bottom, you just have centimeters. Now, I'm going to stop there. I'm showing you this just so you have some idea of what the book is doing. But like I said, in real life, that's not something you're going to encounter. the units we did up above are something you're going to encounter. But for those of you that want a challenge, there are problems in the book where they take it to that extreme like that. I'm not going to say anything more about dimensional analysis until we start actually using it in practical examples. Yeah, sure. Yep. Yep. Just one? Well, because this one and this one cancel out, but there's still one here. So on top I've got one, and then I still got the centimeter on bottom. Like I said, I'm putting it out there so that if you want to try that part of the assignment in the book, you can. But by no means is that something that's gonna like end your career if you don't know how to do it. That's the great positive outlook to put on something as I'm teaching it to you, but I do try to be practical some days. Okay, so we need to start measurement. Our units of measurement. Well, we're going to start out with standard units. And I'm going to talk a little bit about length just because the origin of the units of length is kind of interesting and helps us understand how measurement really works. Measurement was never something up until, at least not up until modern times, was never something that was thought about a whole lot. It was something that came out of need, a necessity. And the necessity was really to communicate. You know, if you and I were trying to make something, build something, and we wanted them both to be the same, if we're in the same room together, that's easy to do. We can compare and make sure they're the same size and all that. But if you're across town or in a different town or whatever, making sure those are the same size, we need some way to communicate that. Now, I suppose you could cut like strings or whatever and send them and say, this is how big it is, but that's not very efficient either. So let's say the piece is going to be the size of my sheet of paper here. You could take your pen and say, okay, that's 1, 2, a little bit under 2 pens long. Well, then I could send that to you and say, okay, it's just under 2 pens long. Well, you could take your pen, this is the fancy WITC dart pen, and you measure, okay, 1, 2. Well, there's where your 2 pens comes out to be. That's considerably shorter. What happened? Pens were a different size. So to make measurement work, there had to be 2 things that were true. One is both people had to have one of those objects. In this case, we did both have a pen. But the second thing was they had to be pretty close to the same size. So they chose things that everybody had and was relatively close to the same size. And for length, that turned out to be parts of the body. What unit would we normally measure this piece of paper in? Inches. An inch was the distance from the end of your thumb to the point of that first knuckle. That was an inch. So you could measure this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 and a half or 11 inches. My thumb's a little big. It should be 11 inches, right? So the thumb was used for inches, and pretty much everybody had at least one thumb. And this was all developed thousands of years ago. The average height of a male was probably in the low 5-foot range. So variation from one person to the next was not near as much as it is today. Getting larger than that, what's our next largest unit of length we use? A foot. Now we have 1 foot equals how many inches? 12 inches. And the foot is exactly what it sounds like, the distance from the tip of your longest toe to the back of your heel. Well, the foot was originally used for measuring things along the ground. Now, if we wanted to measure the height of this wall, what unit would we normally use now? Feet, yeah. I'm not going to take my thumb into it because that's just too much. You notice when I was using my thumb on the piece of paper, I kind of got to guess when I move it. Well, going up a wall, when you have a lot of those Every time you move it, there's a little bit of error. So that could be a huge error measuring something as large as that wall. So that wouldn't be a good idea. However, if I'm going to measure this wall with my foot, I can get to about here with some really serious stretching. I'm not making it to the ceiling unless I chop my foot off at the ankle, am I? So, what's that? Well, I suppose now I could take off my shoe, but at that time, it wasn't necessarily a huge option either. So using my foot to measure things that went up and down like this was not very practical. Like I said, the foot was used to measure things near the ground because feet are usually near the ground. To measure something up and down like that, they used hands. The hand was the width of the hand at the base of the fingers, typically about 4 inches. Now, we don't use those anymore because we have rulers and measuring devices rather than having to use our body. But that was, they had to develop that vertical unit. It's still used, by the way, for livestock, sheep, horses, cattle. They measure their height in hands. It's just a traditional thing. Some of the units have stuck on for traditional, but they're not necessity anymore. Now, a little bit of a historical note. In the 500s, King Edward, a little bit of an egotistical move, declared his thumb and his foot and everything else were going to be the official measurements of the land. So they came in and they cut, little blocks of wood or whatever, the size of his thumb and the size of his foot, and they passed those out for everybody to use for measurement. And even though it was a pretty, like I said, an arrogant move on his part, it was a huge thing for the advancement of measurement, because now I no longer had to get my foot to the top of the wall. I could take this block of King Edward's foot and I could measure, and now I could measure up as high as I could reach. I didn't have to get my foot there. In fact, it was that move that made it so they started using rulers. They started, well, if I've got this block, I can just take a stick and mark it off and compare it to that. So it did cause a huge advancement in measurement. Now, King Edward's foot did not have 12 of his thumbs in it. It was a couple hundred years later that they decided, okay, you measured an object in inches, I measured it in feet. It would be really nice if we could compare to figure out which one's bigger without having to remeasure them. So they adjusted the length of the foot and the inch to make 12 inches fit into a foot so that you could convert between them. But up until that point, nobody ever thought of using them together. These things were measured in inches and these things were measured in feet, and if you wanted to compare, you'd have to remeasure one of them in the same unit. Now, going up, there are other units that kind of disappeared. How many of you ever heard of a cubit? Cubit. Cubit was from the tip of your longest finger to the point of your elbow. At that time, most people's cubit was about 16 inches. In construction, all your stud spacing, your floor joist spacing, bless you, traditional rafter spacing, all that was a cubit. So that's how that was done. Now, think about it, we measure in feet or inches now, but back then you either have to do a lot of inches or 1 1/3 feet. That's kind of hard to guess. So they had a unit specifically for that. As we go larger, what's our next unit? The yard. Yard equals 3 feet. Now, a lot of people think of the yard as the length of a person's stride, and it is about a yard, but the yard actually comes from, take a step, it's 3 feet. No, short legs. The yard actually is a tailor's unit. It comes from, it's the distance from either the center of your chest or the tip of your nose to your outstretched hand. If you've ever seen some, if you've ever ordered fabric, you see some, they'll grab on, that's 1, 2 yards, and they pull it out like that. That's what a yard is. And of course, King Edward declared his reach to be the official yard as well. And those had to be adjusted. Larger than a yard, there was things like a fathom. Fathom is 6 feet. It was used for navigation. A fathom was the shallowest water that a boat, the most of your seagoing vessels could navigate through without getting caught on the bottom of the water. The way they measured that literally was they took the tallest sailor on the ship and threw him overboard. And if you could see his head through the water, at the top of the water, it was too shallow. Now, I'm hoping they pulled him back in, but who knows? It was a different time back then, so who really knows? Everybody line up. Somebody's squatting down because they know they're the tallest. Bigger than a fathom, there's one that I'm going to put on here called a rod. A rod is 5.5 or 5.5 yards, or 16.5 or 16.5 feet. A rod was a shepherd's tool. The shepherd actually had two tools, a rod and a staff. The staff was that hook, kind of like Little Bo Peep has. It was used to hook the animals around the neck so you could shear the wool or attend to any medical needs or whatever. The rod was a defensive weapon. And it literally was a sapling tree. They'd cut off the tree, debranch it, and that's what they used to fight off wild animals that were threatening the herd. So you think about it, 16 feet is 16.5 feet, seems kind of long, but if you're fighting off a wolf or a bear or whatever with a stick, you do want a little bit of distance. So how it got used for measurement, well, let's say that, well, we'll pick on Ashley because that's the name that's on the top of my pile over here. Let's say Ashley has sheep and I have sheep and they go down in the valley and they're pasturing. And at the end of the day, I say, well, I have 15 sheep. And Ashley says, I've got 12 sheep and there's only 20 sheep down in the valley. But one or both of us is lying, right? And of course, there were some fights over that. With cattle and horses, they settled this by branding them, put a permanent mark on them. Sheep, it didn't work so well for a couple of reasons. One, the wool grew out a little too thick. You couldn't see it. Two, I don't know why I find this so humorous, but wool is kind of flammable. So it makes you wonder how many times they tried it before they figured that out. Well, they did start the ear tags, but before the ear tags, the technology became common. What would happen is we would find some major landmark, maybe a rock somewhere, and we would divide it up. Say, I'm going to pasture my sheep over here, and Ashley's going to put hers over here. And if we were worried about the size of the pasture, so I'd take my rod and I'd lay it down on the ground, and there's one rod. We'd take Ashley's and lay it down, there's two. We'd flip mine over, three, and we'd count out. We'd measure out the land. Okay, we've got 40 rods by 120 rods, and yours is the same, so we're equal. To this day, if you look at official land surveys, land is marked out in rods. Bigger than rods, there's things like furlongs and stuff like that. We're going to jump up to miles. Anybody remember how many feet are in a mile? There you go. 5,280. Or in yards, 1,760. The mile actually comes from, I've heard a couple of rumors of where it comes from. One of them was the distance King Edward could see out the window from his throne. The one that makes the most sense to me, that I think is most credible, is it was a Roman military. A mil, the Greek prefix mil stands for 1,000. Like if you look at your tax rates, the mil rate is the amount you pay per $1,000 of value. A mile was the distance of Roman soldiers marching in formation. A pace was starting on your left foot, going to your right foot, and coming back to your left. So a mile was 1,000 paces of a Roman soldier marching in formation. So we got these weird units here. If we want to convert from one to the other, well, if I throw out 4 feet and I want to convert it into inches, many of you could probably just rattle that off as what? 48 inches, which is multiplied by 12, right? If you didn't know that off the top of your head, that's where this dimensional analysis comes in. Now, we're combining dimensional analysis along with another concept that we learned back when we started fractions. Like if I had 3/4 and I wanted to rename it, remember we did something like this, multiplied by 3 over 3, give us 9/12. This thing was called a unity fraction. A unity fraction equals 1. The technical definition is the numerator is equivalent to the denominator. When you multiply by 1, it can change the appearance, but it doesn't change the value. 3/4 and 9/12 have exactly the same value. Well, down here, my unity fraction is going to look like this. 12 inches on top and 1 foot on bottom. Now that doesn't look like it equals 1, but it does. 12 inches is equivalent to 1 foot. So that is 1. Now, how did I know to put the feet on bottom and the inches on top? Well, that's where the dimensional analysis comes in. I want to get rid of feet and turn it into inches. Well, by putting the feet on bottom, they will cross cancel out. And now what's left? I have 4 times 12 inches is 48 inches. On bottom, I have 1 times 1 is 1. So 48 inches over 1, or just 48 inches. Again, feet and inches, we probably don't need to use a conversion. But let's say I give you 99 feet, and I want to convert it into rods. That's not one that we've used enough to really be comfortable jumping in and doing it. But I can make my 99 feet into a fraction by just doing 99 feet over 1. In my conversion factor, in my unity fraction, what unit is going to go on bottom here? Feet, so they'll cancel out. And on top, I'm going to use rods. Now, to find the relationship between them, first thing I usually do is find which unit is larger. What's the larger unit there? The rod. So that one's going to be the 1 rod. Bless you. 1 rod is how many feet? 16.5. So the feet do cancel out. 99 times 1 rod is 99 rods. 1 times 16.5 is 16.5. And now we have to divide this out to get our answer. 99 rods divided by 16.5 is 6. Okay, it is break time, so let's go ahead and take our break. It is 11:21, so let's come back at 11:31. Okay, so I want to talk about, again, sticking with standard units. They used to be called the standard English units, by the way, but England switched over, I think, in the late 80s to the metric system. The United States, for about 30 years, the United States has been the only industrialized nation that is not on the metric system. Now, in the medical fields, that change has happened, but you do still see some standard units out there. But let's go ahead and zip through the rest of our standard units quick, and then we'll talk about metric. Before we can talk about weight, I want to talk a little bit about what is the difference between weight and mass. They tend to get used interchangeably, but there are some key differences between them. Mass is actually, the scientific definition is the amount of matter in an object. It literally how many particles, how many atoms are packed into it is its mass. Weight is a measurement of force. It's the force of gravity on an object. The two of them are very closely related because obviously the more mass an object has, the more gravity is going to pull on it. So increasing the mass does increase the weight. However, there are some important differences. The big difference can be shown in how they're measured. Mass is measured with a balance. So balance is basically a teeter-totter. You put the object we're trying to measure on one side, and on the other side we put known masses until it balances. And when it balances, whatever the mass is on this side is equal to the mass of this object. Weight is measured somewhat differently. Weight is usually measured with a spring. And a spring will stretch depending on how much force is on it. You double the force, a good spring will stretch twice as much. So we usually have On that spring then is a scale. A scale is just a metered out set of numbers. And then some sort of an indicator that indicates the position of that spring. If we add a weight then, hang our object that we're trying to measure on that scale, it stretches out, and that indicator moves, telling us how much the spring is stretched. So that literally measures the force, the pull of gravity on that object, how much stretches the spring with that object hanging on it. Now, again, you might think, well, both of them are using gravity to measure them, because without gravity, this balance can't balance either. But the difference comes if we go to a setting where gravity is different. Like if we go to the moon, where gravity is like 1/6 of what it is on Earth, our object and that known mass are still going to balance, because the amount of gravity on our object is going to decrease, but the amount of gravity on our known mass is going to decrease the same. So they're still going to stay balanced. So the mass doesn't change. However, if we take our scale to the moon, gravity is pulling less, so it's going to stretch that spring a lot less, so the weight changes. On Earth, gravity is relatively constant. There's about a 9% difference between the equator and the North Pole as far as the amount of gravity. So a 200-pound person would literally be like 16 or 17 pounds heavier on the North Pole than they are on the equator. So that is a little bit of a difference. You want to go to the equator? Oh. What's that? Yeah, go to the moon. You'll go to the moon. I'll be under 50 pounds. So anyway, there you go. I like that philosophy. That sounds like a T-shirt there. So anyway, on Earth, because gravity is close to constant, we tend to use mass and weight interchangeably. Now, in the standard system, there is a unit of mass. The unit of mass, I'm guessing you've probably heard it, but didn't realize it was a measurement unit. It's a slug. Well, you ever hear the term, well, I got a whole slug of them sitting at home or whatever? The slug is, one slug is about 32 pounds. So it's a relatively large unit. Yeah, it's about 32. It's a little bit off, but it's about 32. We won't ever use a slug in here, by the way. A slug outside of engineering almost never gets used. The unit of weight, of course. What's our largest unit of weight that we use? A ton. Perfect. A ton is how much? 2,000 pounds is what we most commonly refer to as a ton. That is what is referred to as known as what? One net or short ton, which implies that there is something called, and you don't need to write this next one down, a gross or a long ton. A long ton or a gross ton is 2,240 pounds. The difference, think of your gross pay and your net pay. If you work 40 hours in a week and you're paid $15 an hour, that's a gross pay of $600. But you don't get that much, do you? So they take out taxes and other things, and you might get $400 out of your $600. Same thing here. Tons was originally used for measuring grain, buying and selling grain, but you can't put a ton of grain on a scale without it falling off. So you had to have some sort of a container. The container that held a ton of grain was about 240 pounds. Smaller than a ton, of course, we have the pounds. The abbreviation for pounds would have made sense to use PD, but unfortunately in the bookkeeping system for buying and selling grain, PD was already used as the abbreviation for paid. So to avoid confusion, Well, lb comes from the Latin word for pound, which is libra. Smaller than a pound is half a pound. Yeah. Smaller than a pound, you're right. The ounce is the next unit. There we go. Technically, you are correct. How many ounces are in a pound? 16 ounces in a pound, yes. The abbreviation for ounce also came from the Latin word for ounces, and I don't remember what it is, not what the word is. The abbreviation is OZ. I don't remember. I usually know the Latin word for ounce, and I can't remember it right now, but it doesn't matter. There are units smaller than an ounce. I don't want to know what you do on your weekends. Okay, 1 ounce is 16 drams. A dram sounds like a metric unit, but it's not. It was the original apothecary unit. You might be prescribed an eighth of a dram of a medication, or a 16th of a dram, or even a half a dram if it was serious. Smaller than a dram, there was a grain. And the grain is one that's going to be important. There are 7,000 grains in a pound. They really did. They actually did take a tweezers and count grains of powder and count out 7,000. Well, they didn't have television back then, so they were a lot more productive. This one's going to be big because to be honest, the conversions we do with grains are going to be into the metric system because the grain was so entrenched into medicine and the pharmaceutical side of it that they absorbed grains into the metric system. Now, it was a very ugly absorption, and we'll go over that in a little bit because what they absorbed in the metric system isn't a grain, but we'll talk about that. Now, you hear on the news a lot, gold is up to $1,700 an ounce or whatever. Now, you don't need to know this, but I want to put this out there just as an educational thing. We talked about King Edward saying, his thumb and whatever were going to be the official units. Other rulers around the world had that same idea and made that same declaration, my thumb, my foot, my whatever. So standard measurement from one country to the next was anything but standard. The foot was not the same from Switzerland to France or whatever. Same happened with other units, pounds and ounces and stuff like that. Well, the center of trade in the world for precious metals was the island of Troy. So, what's that? Well, the Troy is actually an island in the Mediterranean Sea, just off the coast of Greece. You ever hear of the Trojan War, the Trojan horse? That was the island of Troy. The Trojan horse is a myth, but yes, but the island itself is real. But anyway, because that's where they were bought and sold, we actually still use Troy units, Troy measure for precious metals. 1 Troy pound is only about 0.82 of our standard pounds. However, 1 Troy pound only contained 12 Troy ounces. So a Troy pound is smaller than a standard pound, but a Troy ounce is actually larger than a standard ounce. So just so you're aware of that. Next we have, again, we have to have another one of those discussions about volume and capacity. There is a difference between volume and capacity. Capacity is just a standard size container. And it really is how much something can hold is its capacity. Volume is a length times a times the height. It's actually derived from length measurements. A volume might be a cubic foot or a cubic inch. Those are volumes. Gallons, quarts, all those things are capacities. So you hear a lot about volumes, and generally what they're referring to are capacities. Gallon is capacity. So a gallon, we'll start off with that. A gallon, believe it or not, actually came from the amount that could be held in a men's hat. Now, I'm not talking about a cowboy hat. You're talking about your standard dress hat that was common in Europe at the time was about a gallon of material. No, that's a stovepipe hat. That was huge. Talking about like little derby hat type deals. In fact, they referred to cowboy hats when they first came out as 10-gallon hats. That was a sarcastic. They didn't really hold 10 gallons. It was just a sarcastic comment of, boy, that's a 10-gallon hat there. Yeah. But a gallon was just that size. Bigger than or smaller than a gallon, we had quarts. How many quarts are in a gallon? 4. The word quart actually comes from the word quarter. It was originally called a quarter gallon and is slowly abbreviated to quarts. So a quart actually derived from the gallon itself. Smaller than a quart is a pint. Now, a pint was a separate unit. A pint was actually a standard size container for, well, not container, but a glass for drinking. And there are 2 pints in a quart. That size had to be adjusted so that it fit in, so you could convert pints to quarts. Smaller than a pint, we have cups. How many cups are in a pint? 2 cups in a pint. A cup actually is your cupped hand, what you can hold in it. Usually it was for dry measure, powder, sugar, or whatever. Flour, sugar. You stack it up, and when it's heaped up in the cupped hand, that is 1 cup. I have a friend of mine who's a caterer, and I've double checked her before when she does that, and she's dead on every time. It's exactly 1 cup. Smaller than a cup, you said it over there. What was it? Ounces, and technically use fluid ounces. There are 8 fluid ounces in a cup. Very good. A fluid ounce and a dry ounce are somewhat different. A fluid ounce is the size of 1 ounce of water. There are units smaller than a fluid ounce, not necessarily hugely important to medicine anymore, but they used to be. Yes. Anybody know how many tablespoons are in a fluid ounce? There are 16 tablespoons in a cup. 8. There's 8 ounces in a cup, so there's 2 tablespoons in a fluid ounce. 2 times 8 gives you the 16. Tablespoon is a tricky one for abbreviation because I always abbreviate it TBSP, but it can be abbreviated just capital TSP or just capital T. What's that? Capital T always indicates a tablespoon. Now you can do a small t BSP is still a tablespoon. That's it right there. 1 tablespoon is 3 teaspoons. A teaspoon is always abbreviated with a small t, either a small TSP or just a small t. In fact, the most common one now is capital T for tablespoon and small t for teaspoon. That is kind of confusing, so be careful of those. Trust me, speaking from experience, unfortunately, if the recipe calls for 3 teaspoons of salt and you put 3 tablespoons of salt in your chocolate chip cookies, yeah, I mean, I'm a large man and have not thrown away too many cookies in my time, but I could not choke those down. Now, the next couple of units I'm going to throw out here are, again, just for information, but just because they're interesting, smaller than a teaspoon, 1 teaspoon contains 2 dashes. A dash, you have your salt shakers now, but they used to have the big spice shakers that were like a big salt shaker with bigger holes. A dash was literally one little tilt and dash of the shaker. 1 dash contains 3 pinches. Literally, you stick your finger into the powder, the flour, whatever, you pinch them together. What's between them goes in the recipe. That's a pinch. 1 pinch contained, this is the one that I think is kind of a little disgusting, 2 smidgens. A smidgen is you just stuck your finger in there, and whatever stuck to your finger, you flicked into the recipe. Well, I'm thinking the cook with sweaty fingers had big smidgens. Yeah, most likely. So anyway, oh yeah, it gets up to. So now there is a relationship between our capacity and volume. 1 gallon, again, approximately, notice I didn't put an equal sign, I got the wavy equal sign, 231 cubic inches. 1 gallon is approximately. That's what the symbol means, is approximately. Or 1 cubic foot. Yeah, so just a wavy equal sign. This means it's not equal, but it's close to. 1 cubic foot is technically 7.48, but we're just going to say 7.5 gallons in 1 cubic foot. Okay, so there were other units that came involved, like minimums and stuff like that are kind of outdated now that we're not going to talk about, but they were used as capacities for medications as well. Let's get on to the metric system. A lot of people groan over the metric system, but it's actually, once you get used to it, it's very simple to use compared to the others. Now, I talked about the standard systems coming out of that need and the units never being intended to work together. And it was years later they finally adjusted them so there was a conversion. But because of that, it's very awkward. 12 inches in a foot, 3 feet in a yard and all that, 16 ounces in a pound. It was evolved and it was forced to be units that work together. We forced them to work together and they were never planned that way. Well, the metric system, literally they had thousands of years of experience measuring, so they were able to look at what happened with the standard system, look at what worked well and what didn't work well, keep the things that worked well and build on them and fix the things that didn't work well. One of those things was that the conversions were poor. So they came up with a standard number that was the conversion for everything. Also, the several different units was a problem. So there's only 1 unit of measure for each type of measurement. For example, for length, the only unit of measurement is a meter, abbreviated with an M. For capacity, it's a liter. Now, I was always taught you abbreviate liter with a capital L. I found out years later the reason for that. I learned the metric system when I was in middle school in the late 80s, 1980s, by the way. What's that? Well, at that time, a lot of your typewriters, the small L and the 1 were hard to distinguish. And some of the old typewriters before my time didn't even have a 1 key on. You just used the small L, lowercase l. So is that 51 or is it 5 liters? If you use a capital L, it's obviously 5 liters. So to avoid that confusion, they said you use a capital L. So you'll still see me use a capital L most of the time. But it is okay to use a small L for liters now. For mass, actually, let's do weight first. What's the unit for weight? Anybody know? It's a Newton. In the standard system, we had the slug for mass, which most people have never heard of, because in the standard system, we tend to focus on weight. In the metric system, they use Newton for weight, because in the metric system, we tend to focus on mass. The unit for mass is the gram, abbreviated with a G. That is an N, capital N for Newton, sorry. You'll probably never see Newtons in use, unless the only time you'd ever see Newtons in use is if you got into prosthetics. The engineering and design of prosthetics would use Newtons. So then the metric system, you have that main unit, the meter, the liter, or the gram. Now the meter is slightly longer than the yard. A meter is like 39.4 inches. And I always thought it would be so much more convenient if they had just made the meter equal a yard. Well, remember what I said about different liters and different declarations? Well, the meter is the Swiss yard. The metric system was developed in Switzerland, and that was what their yard was. So it is equal to a yard, just not the one we're used to. If we want to measure something smaller than a meter or a liter or a gram, they used prefixes. The prefix deci meant 1/10. So a decimeter or deciliter or decigram was 1/10 of that unit. The prefix centi was 1/100th. So cm for centimeter, cl for centiliter, or cg for centigram is 100th of a meter or liter or gram. Milli, kind of like the mil for mile, is 1/1000th. So mm is millimeter, ml is milliliter, mg is milligram, is 1,000th of their main unit. Now at that point, we stopped going by every 10. We went 10, 100, 1,000. We didn't do the 1/10, the 10,000th, or the 100,000. They didn't put a unit in there for those. They skipped them, and they went straight to the 1/1,000,000th. The 1/1,000,000th was micro, was 1/1,000,000th. Now the abbreviation for micro is actually the Greek letter mu. It looks like a U with a long tail in the front, or a P with an open top. However, in the medical fields, one of the first places where they started to keyboard all their information into the computer, there is no mu key on the computer keyboard. And rather than having to go through a menu to select that so you could enter that information, they used MC. So micrometer was MCM, microliter was MCL, microgram was MCG. You might still see, that mu L for microliter or MCL, either way. They're trying to push to get the mu used more, but the medical field still is predominantly MCL. Smaller than that, we would jump to a billionth, and I'm not even writing this down because I won't test you on it, is a nano. A nanometer is a billionth. It's extremely tiny. You heard a lot of about 10 years ago about nanotechnology and nanoscience. That's all it was the science of things that were really small. One atom is about 1/10 to 1 nanometer in size. So you're talking about building things on the size of an atom. If you wanted to measure things that were larger, significantly larger than a meter, we had prefixes that made them larger. Deca stood for 10. Now, since dm was decameter or decimeter, they used dam for decameter, and dal for decaliter, dag for decagram. So that was 10 meters or liters or grams. Just 10. DAM is decameter. DAL is decaliter, yep. And DAG is decagram. That's okay. Hecto meant 100. So HM was a hectometer, 100 meters. HL was 100 liters. HG was 100 grams. And then the big one, kilo, means 1,000. Kilometers is 1,000 meters. Kiloliters is 1,000 liters. And kilograms is 1,000 grams. And then just like on the other side, we didn't do 10,000 or 100,000. We jumped up to the 1 million, which is mega. Notice I spelt mega with a capital M, because when you abbreviate mega, we abbreviate it with a capital M. A megameter is capital M, little m. It's 1,000,000 meters. A megaliter or a megagram. Now the megagram is 1,000,000 grams or 1,000 kilograms has been labeled a metric ton. So when you hear metric tons, that's what I'm talking about. Have a good weekend. So those are our units. To convert within the metric units, it's actually quite simple. Because every position on this chart is multiplying or dividing by 10, when you multiply or divide by 10, all it does is move the decimal point. So converting units is simply moving the decimal point. Now, one thing I'm going to note here, you've probably heard these main units, the meter, the liter, and the gram. And you've surely heard milliliters, millimeters, milligrams, and kilometers, kilograms. The other ones you probably haven't heard so much because they developed all these and then they realized that they didn't really need them later. So hecto is almost never used. The only thing that hecto has ever been used for is actually in land measurement, like acreage type measurements. Deca, you don't hardly see. I've seen a couple of minor uses of deca. You don't see centiliters or centigrams hardly at all. You see centimeters in the United States, mostly because it's what's closest to an inch, because the inch is so ingrained in us that we kind of adopted the centimeter. But normally if you go to Europe where they're more fluent in the metric system, millimeters get used way more than centimeters do. And in the medical fields, deciliters get used a lot. Your blood tests, like blood glucose, if that shows 90 is your blood glucose, that is 90 milligrams of blood glucose per deciliter of blood. That's what that reading is saying. Another handy thing about this is it was planned out. I showed you up above 1 gallon is like approximately 231 cubic inches. Well, here 1 milliliter is defined to be 1 cubic centimeter. So 1 centimeter by 1 centimeter by 1 centimeter is a milliliter. 1 gram, I shouldn't put the R on there, 1 gram is equal to the mass of 1 milliliter of water. So the units of length, capacity, and mass are related to each other. So you can very quickly convert between them even. So let's do some conversions here. Let's say I have 7.2 meters and I needed to convert into centimeters. On the chart, to get from meters to centimeters, I have to move 2 spots to the right. Well, to make the conversion, I would take my decimal point. I would move 2 spots to the right. Adding a 0 in there makes it 720 centimeters. So the movement on this chart is just the movement of your decimal point to make the conversions. We always start with the first unit. This first unit was meters, so we started with meters. Yep. But it could be like 32 centimeters going to millimeters. So here's centimeters, I'm going to millimeters. So I'm going to start here and go to millimeters. Yeah, so you start whatever this first unit is where you start. And you go to where the second unit is. Because we are converting from centimeters to millimeters. So we start at centimeters and go 2 millimeters. Oh, sure. So yes, one spot to the right. So my decimal point goes one spot to the right. We have to add a 0. It is 320. Or if we have 750 milliliters, and I want to know how many liters that is. From milliliters back to liters is 1, 2, 3 spots to the left. Perfect. My decimal goes 1, 2, 3 spots to the left. 0.750. It isn't terrible, really. Let's take a look at compound units. Assume it's PSF to OSI. What this really is 72 pounds per square foot. And I want to convert to ounces per square inch. Ounces. Yeah, that's OZ. When we talked about our rates, remember we said you have to think of that 72 pounds per square foot as 72 pounds over 1 square foot. Now, we didn't really talk about converting units of measure, but we have to change our pounds, or units of area, I should say. We have to change our pounds into ounces, so we'll do that first. If I'm getting rid of pounds, where am I going to put them in my conversion factor? On bottom. Of course, I'm going to ounces. Relationship, 1 pound, 16 ounces. So the pounds cancel out. Right now, the units I have, and look, what unit do I still have on top? Ounces. What unit do I have on bottom? Feet, square feet. So I want the ounces on top. That's good. I have to change that square feet into square inches yet. I do another conversion factor. Now the square feet are on bottom, so to get rid of them, I have to put them on top. And I'm converting them into square inches. Now, as I said, we didn't talk about units of area, so I'm going to give you this conversion. 1 square foot is 144 square inches. It's 12 inches by 12 inches. So now the square feet cancel out, and those are gone. So what we have is 72 times 16 ounces, which is 1,152 ounces on top. On bottom, 1 times 144 inches squared is 144 square inches. So we divide that out. 1142 divided by 144. We get 8 ounces per square inch. Let's say I tell you that I can throw a baseball at a rate of 90 feet per second. You think I can do that? No. Was that fast? Well, 90 feet per second is 90 feet over 1 second. What units are we used to seeing speed expressed in? Miles per hour. So we need to get feet into miles and seconds into hours. So which one do we want to do first? Feet. Okay, so we're going to put feet on bottom so they cancel out. Going into miles. 1 mile is 5,280 feet. So the feet are canceled out. Now we have to get rid of seconds. Where are the seconds going to go here? On top, and we're converting to hours. Do we have a direct relationship? Yes. One hour is 3,600 seconds. If you didn't see that, we could go to minutes. 1 minute is 60 seconds. The seconds cancel out. Then we just have to add another conversion factor from minutes to hours. 1 hour is 60 minutes. Notice what I've done here. This is dimensional analysis. I'm putting the units here so that they'll cancel out the other units. And notice right now what I have. The only unit that's left on top is miles. The only unit that's left on bottom is hours. So on top, I multiply out 90 times 1 times 60 times 60 is what? 324,000, I believe, miles. On bottom, 1 times 5280 times 1 hour is 5,280 hours. And now we do have to divide that out. Was that like 61.4, 61.36? The 61.36 I remembered from before. I've done that one before. Okay. Now do you think I can throw that fast? Maybe. Question. I'd have to do a lot of warm up. I could probably still throw that, but maybe only 4 or 5 pitches, and then I'd have to rest. This is a tough process. Now for you guys, I wanted to show you the standard unit conversions here. For you guys, most of what you're going to do is in the metric system. All right, let me grab. I'm getting the equivalent. So if you wanted to convert this type of stuff in the metric system, you might have something like 72 milligrams per liter, and you want to convert it into milligrams per milliliter. Now our metric units, we don't use those, don't have to use those conversion factors, right? We didn't use the dimensional analysis there. Now the book was still, the reason I did it this way with these standard units is this is the way the book does it for metric units too. So I wanted you to see how to do it. And I do usually get that reaction. It is kind of confusing. You need a lot more time to look over it and practice it to make it practical. The way I do it with metric units is to just convert each unit. 72 milligrams per liter is 72 milligrams over 1 liter. Now I am changing milligrams to milligrams. It's not changing, is it? That's still 72 milligrams. Liters are changing to milliliters. If you look on our chart, oops, deci, centi. From liters to milliliters is 3 spots to the right. If you take that decimal point, you go 3 spots to the right, would be 1,000 milliliters. Now I just divide that out. 72 divided by 1,000 is 0.072 milligrams per milliliter. A lot simpler, isn't it? Hopefully. Or you might have 750 grams per liter. You need to convert it to milligrams per milliliter. So again, I write it out as 750 grams over 1 liter. So grams to milligrams, yep. Grams to milligrams is 3 spots to the right. So that would be how much? 750,000. Liters to milliliters, 3 to the right. So that's going to become 1,000. If we divide those out, 750 milligrams per milliliters. So both units change, but the number ends up being the same in the end. You might have 2.5 grams per centimeter. I want to know what is that in milligrams per millimeter. I want you guys to try that one quick. I'm going to give you about a minute as I write that down. So 2.5 grams becomes how many milligrams? 2,500, 2,500. 1 centimeter becomes how many millimeters? 10. Just one spot to the right. Divide that out as 250 milligrams per millimeter. Yeah, I think so too. The book still does that dimensional analysis like I did with those first standard measurements, and I think that's just extremely confusing. Now we've got 3 minutes left, so I've got to talk about one last thing, and that's temperature. We've already really seen the conversions for temperature, so I just want to make a couple little notes here quick. Temperature, our benchmarks are, of course, when water freezes and when water boils. In our Fahrenheit system, the standard system, what temperature does water freeze? 32 degrees Fahrenheit. What temperature does it boil? 212. In the Celsius system, what temperature does water freeze? 0 degrees Celsius. Boil? 100 degrees Celsius. The Celsius temperature system used to be called the centigrade for 100 divisions, 100 gradients. Now the problem with this, all of our other measurements had a common 0 point. 0 centimeters equals 0 inches, equals 0 feet, equals 0 meters. 0 length was 0 length, no matter what unit you were using. Weight, 0 grams is 0 pounds is 0 whatever. The temperature system doesn't have a common 0 point. We can't just use those common conversions. So we have your degrees Celsius from Fahrenheit. So from Fahrenheit to Celsius. To get the Celsius temperature, you take your Fahrenheit temperature, you subtract 32, then you multiply by 5/9. If you're going from Celsius into Fahrenheit, you get your Fahrenheit temperature by taking your Celsius temperature times 9/5 and then adding 32. Now, we talked about these formulas a couple of weeks ago with our basic algebra. So if I give you a temperature of 80 degrees, now let's do one that'll work well. It'll work. 80 degrees Fahrenheit, let's convert it into degrees Celsius. So we're going from Fahrenheit into Celsius. So Celsius is 5/9 times 80 minus 32. So it's just order of operations. What do we do first? 80 minus 32, which is 48. And then 5/9 times 48. 240 divided by 9 is what? What's that? 26.6 repeating. 26 and 2/3, 26.67, wherever you want to round it off at. So now that we've done all these types of conversions, conversions from one system to the other should be pretty simple. For example, 1 gallon is 3.785 liters. So if you have a 5-gallon container, to convert that into liters, put the gallons on bottom, liters on top. 1 gallon, 3.785. The gallons cancel. You multiply it out. Now we're running out of time here, so I want to skip ahead here. If we want to do pounds to kilograms, 1 kilogram is approximately 2.2 pounds. Technically, it's 2.208 or somewhere in there, but we tend to use 2.2 in the medical fields. So if you have a patient who is 143 pounds, put them over 1, and our conversion factor, pounds are on bottom, kilograms on top. 1 kilogram is 2.2 pounds. Pounds cancel out. 143 times 1 kilogram is 143 kilograms over 1 times 2.2, which is 65 kilograms. Okay, that is the end of Unit 2. Next week, the first hour is our Unit 2 test. So some homework to finish up the stuff we talked about today. We have pages 118, 123. Oops, I went kind of backwards there. Page 103, 110, and 114. Covers all the measurement units and conversions and dimensional analysis stuff we talked about today. Next week, I will set aside 15 or 20 minutes at the beginning of class to answer questions on this if you want to. Just like last time, if you want to start early, the test will be at your location. I'll send it out Thursday afternoon, so anytime after the school opens on Friday morning, you can come in and start. Even if you do start early, if you want to check in at 10:30 at the beginning of class, if you have any questions, even if you started the test, I'll still go through examples with you if you have any questions on any of the homework problems. So you guys have a great week, and we'll see you next week.